Have you ever watched fireworks on the 4th of July and wondered why they burn red, white, and blue, or even purple, yellow, and green?
Well, I know that when we see different colors, what we're really perceiving is different frequencies of light. Here, hold this.
Okay.
I want to make some waves. Light is a part of the electromagnetic spectrum to which our eyes are sensitive, and all forms of electromagnetic radiation behave like waves. There are several things about a wave you can measure: wavelength, frequency, amplitude, speed. Of course, all light waves are moving at the speed of light. Amplitude is how tall the waves are. It's measured from the midpoint to the top of a wave crest. The amplitude of light waves determines the intensity of light. Wavelength is the distance between wave crests. And frequency is the number of vibrations per unit time. Frequency is measured in hertz, or cycles per second. Frequency is inversely related to wavelength. The greater the frequency, the shorter the wavelength. Here's an example. These two waves have different wavelengths. If they move at the same speed, which will have higher frequency? The wave with the shorter wavelength has higher frequency.
The color of light is determined by the frequency of the light wave. Red light has the lowest frequency. Green light has a higher frequency. And violet light has the highest frequency of visible light. Color changes as frequency increases or decreases. Try it.
The colors in fireworks are the effect of heat on different elements. You saw this on a smaller scale by placing different elements into a flame. Each element produced a characteristic frequency of light.
Fireworks aren't the only way to create dazzling colors with elements. Neon signs do it too. How do different elements produce these stunning colors?
Remember Thomson's cathode ray tube, where the electrons move from the negative cathode to the positive anode? Well, this is a type of cathode ray tube. I have removed all the air in this tube and replaced it with neon gas at low pressure. Neon, as you can see, glows bright red-orange when a current is passed through the tube. Let's look at some other gases.
So the frequency of light is determined by the gas in the tube. Well, how do these lights differ from, let's say, a light bulb?
Well, a light bulb has a filament. When electricity passes through the filament, it gets hot and glows, producing light. But in this tube, electrons transfer some of their energy to the atoms of neon. These atoms radiate that energy back as light. What I do is use the light-emitting properties of atoms to create works of art. There is another difference between a light bulb and neon light. A light bulb produces white light, which is actually a mixture of all frequencies of visible light. When the light produced by this glowing filament passes through the prism, it is refracted, separating out all the frequencies so you can see the colors. With white light, you get a continuous spectrum. There is a smooth transition of all colors from red to violet without any gaps. Now, watch what happens when neon light is refracted through a prism. Instead of a continuous rainbow, several bands of colors appear separated by gaps. What does this indicate about neon light?
The neon light emits only specific frequencies, so it's not a mixture of all frequencies like white light.
Right. The prism refracts the light into a few discrete spectral lines, each representing a certain frequency of light. This is called a bright line spectrum. Neon has unique spectral lines. So do argon and xenon.
Different elements also emit specific colors when they are placed in a flame. Strontium radiates specific frequencies that we see as red-maroon light. Every element produces a unique fingerprint of spectral lines, like a barcode. This instrument, called a spectrometer, is designed to separate and analyze atomic spectra.
The science of spectroscopy was born from these principles early in the 19th century. By 1860, the spectrometer was an important tool for detecting the presence of known and unknown elements based on their spectra. Spectroscopy works two ways. Atoms that have been excited by heat, as in fireworks, or by electricity, as in neon tubes, emit colored light. When passed through a prism, the light is separated into discrete frequencies that can be analyzed. This is called emission spectroscopy.
The opposite of emission spectroscopy is absorption spectroscopy. Atoms not only radiate light in specific colors or frequencies, they also absorb light of the same frequencies. When white light is passed through a glass filled with hydrogen gas, the continuous spectrum is broken by dark lines at the same frequencies as the bright line spectrum of hydrogen.
Scientists didn't understand atomic spectra and searched for patterns in the lines. Neither the Thomson model nor the Rutherford model of the atom offered any satisfactory explanations of this phenomena. Even so, scientists were quick to put spectral lines to use in identifying elements and discovering new elements.